Okay, the first question asks us to determine if a set of two vectors is a basis for R2. The two vectors being elements of the following set: 1, 1, and 2, 2. Okay, so clearly these vectors are not linearly independent because they're parallel. As a matter of fact, if I multiply the first vector by 2, I obtain the second vector. So the vectors are parallel and thus not linearly independent, and so therefore cannot be a basis for vector space for R2. Okay? There you go. I suppose one of them can be chosen as a basis for a subspace of R2, the subspace being the vector 1, 1. Or 2, 2. We could choose either one of them, and then we could have a vector subspace. But as a basis for R2, those two vectors won't do the job. Okay? Number 2, we have a set of vectors. I'll use a quotation mark because they're not vectors in the usual sense. These vectors are matrices. So we have the set beta of the so-called vectors 0, 1, 1, 0. And let's see, 1, 0, 0, 0, and 0, 0, 0, 1. Now clearly this set of vectors is a basis for the 2 by 2 symmetric matrices. Any 2 by 2 symmetric matrix can be written in terms as a linear combination of these linearly independent vectors. I'll leave it as an exercise to you to show that they're linearly independent. It's very simple. All we'd have to do is say, okay, C1 times 0, 1, okay, and C2 times 1, 0, 0, 0, and C3 times 0, 0, 0, 1. If I set that equal to the 0 vector in the space of 2 by 2 symmetric matrices, that 0 vector will look like this. Okay, and then we can see pretty easily that C1, C2, and C3 must be equal to 0. Obviously, C1, C2, C3 is a solution to this equation, right? If you let C1, C2, and C3 all be 0, so it would wipe out these three vectors, right? These matrices, and we'd obtain the 0 matrix. But the definition of linear independence asks us to see if that's the only solution. So like I said, I'll leave it to you to show that that's true. Okay, that being the case, then we should be able to write any symmetric matrix in the subspace of 2 by 2 matrices as a subspace of the 2 by 2 matrices as a linear combination of these vectors. So let's pick a random element of that space, right? How about the vector, right? I'll use quotation marks again, right? How about the vector 2, 3, 3, negative 4? Okay, now, it's pretty easy to see that we can get constants C1, C2, C3 to equal this matrix, right? Vector matrix. In fact, I'll erase the 0 matrix here, and then we can use the same linear combination. Now, obviously, if C1 is equal to 2, I'll write a 2 here, and C2 is equal to no. C1 is equal to 3, C2 is equal to 2, and C3 is equal to negative 4. We see that we can get this symmetric matrix as a linear combination of these three vectors. Okay? So this is a nice basis for the space of symmetric matrices. See, here we have the set of 2 by 2 matrices, M2 by 2 with real or complex entries, it doesn't matter, and the space of symmetric 2 by 2 matrices with real or complex coefficients is a subspace of this vector space. Okay? So the next question, gives us a set of vectors beta. Okay, so here's a set of vectors beta. All right, so we have negative 1, 1, 1. Okay, or excuse me, negative 1, 1, and negative 1. Okay, and then we have the vector 1, -2, -1. And then we have the vector -1, 5, 8. All right? And so, so what is this? Number 3? This is number 3. Okay. So we want to know if this set of vectors is a basis for R3. All right, well, you know, if we use the definition, we'd have to show that these three vectors span R3 and that they're linearly independent. However, we can use a shortcut. You see, if we have three vectors with three components in them, that means we have three vectors in three-dimensional space. If they're linearly independent, we know that they're going to span. So we don't have to go through the whole span thing, right? To show, you know, that these vectors can, linear combinations of these vectors can reach any vector A, B, C. I mean, if you want to do that, that's fine. You know, that involves a little bit of work with an augmented matrix. But if I call these vectors V1, V2, and V3, right? And then if I take a linear combination C1, V1, C2, V2, C3, V3 is equal to any vector A, B, C, you see what we would have to do, and we're going to do this in two-dimensional space in a moment, but what we would have to do is find formulas for C1, C2, and C3 based on the entries of the vector A, B, C. Right, so for example, we might find out if we solve the an augmented matrix, you know, based on these vectors, right, and this arbitrary vector ABC, we might find that C1 is equal to 2A plus 3B minus 5C or something like that. We did that in class. You know, that involves a lot of work. Like I said, I trimmed that down to do it in two-dimensional space. But, you know, if you want an exercise, you know, maybe that'll give you some extra credit or something, you could solve this. We did something very similar to this in class. In fact, we might have done this exact same problem. But anyway, the moral of the story is you don't have to do this. We don't have to show that these three vectors span three-dimensional space. And the reason we don't have to do that is because, as I said before, we have three vectors with three components that are in three-dimensional space. We only have to check to see that they're linearly independent. You see, if they're linearly independent, then we know they're a basis of three-dimensional space, and we know automatically they're going to span. So we don't have to go through this misery. Isn't that great? I think so. Great. Okay, good. So all we're going to do now is just check to see if these three vectors are linearly independent. Well, it's fortunate that we have three vectors in three-dimensional space because we can use the property that if the determinant of the matrix formed by these three vectors with these three vectors as column vectors, if that determinant is non-zero, then these three vectors are linearly independent. That's a beautiful result, okay? And, you know, it's based on the fact that, you know, if the determinant is non-zero, we'll have an inverse, right? But I won't go through all that stuff. Let's just show that these vectors are linearly independent by computing the determinant. Okay, so we have the matrix -1, 1, -1. 1, -2, -1, -1, 5, 8. Okay, and let's compute this determinant. I'll use the, you know, typical absolute value symbols to indicate the determinant. So we're going to find the determinant by row reducing this to an upper triangular matrix. Okay, so let's go ahead and do that. So, and you know, if we factor something out, we'll bring it in front of the determinant. If we interchange two rows, we'll multiply the determinant by -1, and you know, so on and so forth. So let's use, let's factor out a -1. So I'll factor a -1 out of row 1, and then change the sign of each one of those entries. Therefore, I can use this as our pivot, right? And we can row reduce. So row 2 minus row 1 is what? I'll do, you know, I'll do it all here. You can, you know, you can check to see if this is right. So we have 1 minus 1 is 0. -2 minus a -1 is -1. Okay. 5 minus 1 is 4. Cool. Okay, let's add, let's put some better spacing here. Okay, so let's add row 1 to row 3. Doing so, we obtain a 0 here. Notice that this does nothing to the determinant, to the value of the determinant. Adding a multiple of one row to another doesn't change the determinant. That's a miraculous thing. Continuing to add row 1 to row 3, we have a -2, and then we have a 9. All right? Well, we're not quite there, but we're close. How about I factor out another negative, right? So I can change the sign of here, and then I can remove this negative in front. Isn't that remarkable? There's nothing in front of the determinant. All right, let's add 2 row 2's to row 3. Well, doing so, we obtain a 0, and then we obtain a 1. Huh, isn't that neat? The determinant is equal to 1, because you see, we have an upper triangular matrix, and the determinant of an upper triangular matrix, remember, is the product of the entries on the diagonal, right? So 1 times 1 times 1 gives us a determinant of 1. Well, this determinant is not 0, thus the vectors are linearly independent, thus the vectors are a basis for two-dimensional space. Cool. All right, let's see what we have next. Oh, okay. So now that we know that this is a basis of two-dimensional space, what we'd like to do is find the coordinates of a target. All right? So let's create a target. All right. So we have a target vector of -2, 3, 1. That's our target vector. And what we want to do is we want to find constants. We know they're going to exist because we know this is a basis. So we want to find constants that get us to the vector -2, 3, 1. All right, so we're going to set up pretty much the same kind of a structure, only we're going to make an augmented matrix out of this and solve for, well, okay, so here's what it would look like. C1 times V1, right, plus C2 times V2 plus C3 times V3 equals our target, -2, 3, 1. Again, we know that C1, C2, C3 are going to exist and be well defined because we have a basis. Okay? Yippee. All right, so let's form, so this is a vector equation. Remember, a linear system has 3 forms. One form is equation form, one form is vector form. This is a vector form of a linear system. An augmented matrix is another way to write a linear system, and then in matrix form. We could actually write this problem in matrix form. We can make a matrix out of these 3 vectors, and then solve for C1, C2, C3 by finding the inverse of that matrix. Here, let me just write that down, what that would look like. What that would look like is the following. We have -1, 1, -1, 1, -2, -1, -1, 5, 8. And then we multiply that by the vector of coefficients C1, C2, C3, okay, the coordinates, vector of coordinates, C1, C2, and C3, and we'd like to find the solution. So we could find the inverse of this matrix and then multiply both sides by the inverse of that matrix and obtain C1, C2, and C3. You know, it really is a matter of what you like at this point. But I think I'll go with using the augmented matrix, okay? So anyway, yeah, so, you know, if you want to find the inverse of that matrix, go ahead. I'd be curious to see what it turns out to be. But anyway, let's write this as an augmented matrix, okay? So we have an augmented matrix, -2, 3, 1, all right? So let's solve this for C1, C2, and C3. Notice that we don't see C1, C2, and C3 because they're kind of hidden. They're kind of implicitly represented by the fact that we have, you know, these distinct positions within the matrix. So, when we go to the land of equations after reducing this matrix, we'll see, that we obtain values indeed for C1, C2, and C3. Okay, let's multiply row 1 by -1, as we did before when we were row reducing, right? But this time, you see we have numbers on the right-hand side that we have to be mindful of. So row 2 minus row 1 is 0. Row 2, -2 minus a -1 is -1. And 5 minus 1 is 4. And 3 minus 2 is 1. Okay? Good. So this is -1. I don't want to lose that. All right? And we have, that's just a smudge there and a smudge there. Okay, so row 1 added to row 3 yields the following. 0, -2, okay, and 9, right? And then finally, on the right-hand side, row 1 added to row 3 is 3. So far, so good? Again, as before, when we were finding the determinant, we can multiply row 2 by -1, only we don't need to factor it out because, we're carrying that process of multiplication by -1 to the right-hand side over here. So I have +1, -4, and -1. Now I wanted to do that so I would have a pivot here, an assassin as I like to call it, to get rid of the -2. And I could also use that to get rid of this -1. So let's add 2 row 2's to row 3, okay? So what does that give me? A 0 here. It gives me a 1 here, and 2 of -1's added to 3 is 1. Perfect. How about we use this assassin to get rid of the -4 and the 1, and then finally we can get rid of that -1. So I'll add 4 row 3's to row 2. All right, doing so we get a 0. Okay, and then 4 1's added to this gives me a 3. Okay, next I'll take row 1 minus row 3. So row 1 minus row 3 gives me a 0 here, and then 2 minus 1 gives me a 1. And then finally, if I add row 2 to row 1, I can get rid of that -1 there, right? And then I have to be mindful of the right-hand side. So row 2 added to row 1 gives me a 4. Okay, so that we've reduced the augmented matrix. Now, if we're having a good day, then that would mean that C1 is equal to 4. We go back to the land of equations, as I like to say. C2 is equal to 3, and C3 is equal to 1. Okay, thus, this would be, if we construct a vector with C1, C2, and C3, that would be the coordinate vector of our target with respect to this basis B. Of course, we're going to check that to see if this is right, but the coordinates of the target, -2, 3, 1, relative to beta, is equal to the coordinate vector 4, 3, 1. That's what I want to say, okay? So you take the target and you say, hey man, I want the target relative to beta, and that's going to be equal to 4, 3, 1. Well, let's check it out and see if that works. So that means 4 of vector 1's, -1, 1, -1, all right, plus 3 vector 2's, 1, -2, -1, plus 1 vector 3, -1, 5, 8, is equal to, we hope, to the target, -2, 3, 1. You see what's going on here? 4 times vector 1, right? Here's the 4 here, 3 times vector 2, and 1 times vector 3. All right, let's see if this works. All right, so what do we have? We have -4 plus 3 is -1, minus 1 is -2. Yay, we're off to a good start. 4 times 2 is 4, minus 6 is -2, plus 5 is indeed equal to 3. And negative 4 minus 3 is negative 7, plus 8 is equal to 1. We are indeed having a good day. Okay? So the coordinates of the target, negative 2, 3, 1, relative to our beta is equal to 4, 3, 1. Let me write that so it's clear. All right, good, good, good. All right, next question. Show explicitly, okay, that, oh, no. We have another question. We have a question involving other kinds of vectors, involving polynomials, all right, vectors, all right? So let's see what question 4 has to say. So question 4 says we're going to have a target, right? So here's the target. P of x is equal to some target polynomial, second degree polynomial, x squared plus 4x plus 3, all right? And can that be written as a linear combination of the vectors in S, where S is equal to the set x squared plus x plus 1. So that's a vector, is minus 1 or plus or minus 1. And then we have x squared minus 1, that's another vector. And then x plus 4 is another vector. So, these being our transports, can we get to the target? And if we can, then we could write the coefficients that will take us to that target. Now, I'm not asking if this is a basis. I just want to find out if this target is in a linear span of these three vectors. So let's see. If I write C1 times x squared plus x minus 1 plus C2 times x squared minus 1 plus C3 times x plus 4, can we get to x squared plus 4x plus 3? All right, well, let's collect like terms. So we have an x squared and x squared. Who multiplies x squared? C1 plus C2 multiplies x squared. You can, verify that just by multiplying through. I'd like to multiply through, but in a systematic way where I can organize the coefficients of the monomials x squared, x, and 1. So let's see who multiplies x. Who multiplies x? C1 multiplies x, and C3 multiplies x, right? And now all we have are the constants, right? So we have negative C1, negative C1 multiplies 1, all right? And negative C2 multiplies 1, and 4C3 multiplies 1, right? The monomial 1. Okay, so we want this linear combination to equal this target. Well, if it's going to do that, then we're going to have to equate coefficients, sort of running low on space, but we have 1 times x squared plus 4 times x plus 3. Therefore, we have the linear system. Let me write this down elsewhere. P of x is equal to x squared plus 4x plus 3. All right, let's solve this equation. Well, what do we have? If we equate coefficients, we have C1, C2 is equal to 1. We have C1 plus C3 is equal to 4. And then we have this, combination here is equal to 3. All right, so what does that mean? Well, that means a linear system, right? C1 plus C2 is equal to 1, right? This is a linear system in equation form. And then we have C1 plus C3 is equal to 4. And finally, we have negative C1 minus C2 plus 4C3 is equal to 3. All right? So that's good. So we have a linear system in equation form. Let's write that in augmented matrix form. What is that going to be? We use the placeholders of the matrix to represent implicitly C1, C2, and C3. So we have 1, 1, 0, and then a 1 on the right-hand side. Then we have a 1, 0, 1, and a 4 on the right-hand side. Negative 1, 4 equals 3. Okay, so we take this linear system and we write it in as an augmented matrix, and let's solve it. Okay, and then once we solve it, we hope what we're going to get are coefficients C1, C2, and C3 that are going to transport these vectors to our target, x squared plus 4x plus 3. You see? So let's reduce this matrix and see what we get. Well, we'll use this as the pivot or assassin. So row 2 minus row 1 gives us a 0 here, gives us a negative here. 1 minus 0 is 1. 4 minus 1 is 3. So we have a 3 here. Okay? All right, so let's add row 1 to row 3. Oh, that's nice. We get a 0, we get a 0, we get a 4, and a 4. That makes me happy because I don't have to introduce fractions, at least yet. So I divide row 3 by 4, and I get 1, 1. Okay, then how about row 2 minus row 3? That's going to give me a 0 here and a 2 here. And finally, if I add row 2 to row 1, I have a 0, 0, and a 3. 3, 2, 1. Okay. So I have coefficients 3, 2, 1. Well, what I hope is that when I employ the coefficients, x equals 3. Oh, is that a minus 1? Is that a minus 1 there? Yeah, I guess so. All right, so let's multiply row 2 by negative 1. So that gives me 3, negative 2, 1. Okay? All right, so my constant should be 3, negative 2, 1. Let's see if that works. If I use a 3 here, and I use a negative 2 here, and then I use a 1 here, all right, will I get to my target? Well, the x squares look good because I have 3x squared minus 2x squared, and that's x squared. That checks out. 3x's plus 1x is 4x's, so that checks out. And then negative 3 plus 2 is negative 1, plus 4 is indeed 3. Yes. Okay? So the constants, so this target, P of x, so what do we conclude by this? You see this target, P of x equals x squared plus 4x plus 3 is in a linear span of x squared plus x minus 1, x squared minus 1, x plus 4. Okay, good. I'm not saying that this is a basis. It could be. It could be. There are 3 of them, and this is a 3-dimensional vector space. But I would need to do something else. I believe it is a basis. If I wanted to see if this was a basis, I would do a different equation. Let's do that just for the heck of it. Let's show that this is a basis. All right? Well, okay, so we have 3 vectors, and the polynomial space for second order polynomials is 3-dimensional, because you see we have 3 degrees of freedom here. We could we could pick a coefficient for x squared, we could pick a coefficient for x, and we could pick a coefficient for the constant term, right? So if I did that, C1, C2, C3 is equal to the 0 vector. I'm doing this because I want to show you what the 0 vector looks like in polynomial land. It looks like this: 0x squared plus 0x plus 0. That's the 0 vector in polynomial land. Well, if we were to write this linear system, you see what we would have here is zeros on the right-hand side. And then once we row reduce that linear system, we would find that there are no free variables, and that indeed C1 equals C2 equals C3 is the only solution to this linear independence equation. So now I've shown that this is a we have three linearly independent vectors. I didn't ask you to do that. I just wanted to do that extra for you. But we have three linearly independent vectors in P2, the polynomial vector space of second order polynomials. Okay, fantastic.